everyone. Welcome to Camp 161, Module 2, Drafting Multi-View Drawings. We're going to look at a few techniques, a few of the drawing conventions, how the different drawings are set up, and look at some of the equipment. So this will get us all set up for understanding how the multi-view drawings help us convey the design of spaces, objects, and constructions to our clients, to our partners, to our builders, and to the public as we move forward in the built environment, conversations about the built environment. First slide deck is from John Levine, our colleague from the Department of Landscape Architecture, who has summarized effectively a lot of the key information that found in our design drawing textbook by Frank Ching and Steve Jurasik. So an excellent summary by John. We thank him for that. We begin here with this slide deck, looking at these different pictorial systems and multi-view drawings, the different types of drawings by nomenclature and by name, understanding what the different names mean and what the different drawings do. And so chapters in Frank Ching's book, Design Drawing, are helpful for that. When we think about different drawings across these professions, we classify them in systems according to their method of projection and by resulting pictorial effect. Those are words directly from Ching, and so there are three categories of drawings that we will look at here. The first category is orthographic drawing, the second category is oblique drawings, the third are perspective drawings, and we'll be doing examples of all of these types throughout the semester. The orthographic drawing is an orthographic projection of a building's or object's true length and sides to a picture plane. And those projector lines are parallel to each other and perpendicular to the picture plane. The picture plane is the invisible plane that we can imagine all of these different edges and corners and lines being projected to, so that we can see something in this example in true elevation. An oblique projection, the projector lines are parallel to each other but oblique to the picture plane, so they in fact makes the object or the space or the entire construct appear turned to the viewer. Then perspective, the most natural that we experience in the environment, projector lines converge to a point that represents the eye of the viewer. So when we stand in the built environment or the natural environment, we actually are experiencing perspective. And so perspective drawings attempt to create that perception of all of the different edges and corners vanishing away from us. Orthographic drawings include plan, section, and elevation. Those very typical, that top view or that side view or the two side views, or in the case of section, a cutaway view of an object, space, or construct. And we put those together to represent that three-dimensional subject through those views in what we call the multi-view drawing. There are other drawing types in the category of paraline drawings that include exonometric drawings, isometric, diametric, and trimetric. Oblique drawings, both oblique elevation and plan oblique, are part of the category of paraline drawings, but are different drawing systems within that. And then perspective, we typically talk about 1 point, 2 point, and 3 point perspective drawings that have 1 point, have all of the edges that are parallel to each other and perpendicular to the picture plane vanishing to 1 point, edges that in a 2 point perspective vanishing to 2 points. And then if we're dealing with something either tall or elevated, or if we're looking down at it from the air, we will in fact experience 3 point perspective in the case of skyscrapers or even natural settings like a ravine or a canyon or something like that. We'll start to look at 3 point perspective to represent that. Some of the equipment, we have another slide deck from Professor Franklin that includes more of the equipment. We typically, when we're starting to do our multi-view drawings, we need a pencil or lead holder. We may use technical pens to represent different line weights. The lead holder can be pointed a certain way to create different line weights, either consistently or be pointed to make fuller lines. Technical pens come in different line weights, usually by millimeter or fractions of millimeters, from thin to thick. Drafting tape or drafting dots. The engineer scale and the architect scale, typically a 45-90 or 30-60-90 degree triangles or an adjustable triangle, and a T-square or parallel rule are very typical drafting tools for when we are laying out a project across the three professions. The two scales that we use, one is called the architect scale, somewhat self-explanatory, but it deals with the scales that are typical for architectural drawings in the human to object scale, the scale and materials of furniture, of wall sections, of interior spaces, all the way up to buildings, represent the architectural scale. There are 6 sides to the scale. They are typically, we call them triangular scales or bar scales. They're made of heavy plastic or sometimes aluminum or wood, depending on the age of the user, perhaps, but also the age of the object. I have scales from my father that are wooden, that were made in the 1960s, and they're just as good as new today. The aluminum scales make a great sound when they drop onto the concrete floor of camp. That's just a sound you will never forget. But they are 6-sided because we try to layer together 2 scales on each blade of the scale itself. You can see the 3/16" scale starting here. Some parts of these blades read from right to left, some read from left to right. In the case of the example here, the 3/16" equals 1 foot scale, which is a very good scale for interior architecture or even starting to get into some wall sections, starts here at 0 and then reads on this lower line from right to left. This would represent 0, 2 feet, 4 feet, 6 feet, 8 feet, 10 feet, 12 feet, and so on. If a measurement happens to be, let's say, 2'6", we would use this scale starting from 0 and then read from 0 to 2, and then add the portion of it that's missing to the right. You can see to the right of the 0 are portions of a foot, in this case 3 inches, 6 inches, 9 inches, and 12 inches. So if we had a measurement that was, say, 2'6", like the width of a door, that measurement would include the 2 portion here plus 6 inches that is part of that fractional division here to the right of 0. The other numbers that you see there represent another scale that's found in the blade that reads from left to right. That might be, I'm guessing, might be 3/32 scale because 16 is a division of 32, 32 is division 16, and so on. It might be the 3/8. I might be mistaken. But at any rate, we do like to gather up 2 different scales, one reading from left to right, one reading from right to left. So as you examine your architect's scale, be mindful of which scale you're actually reading. In fact, that some may be reading from left to right, right to left. There is a 16 scale, which represents 1/16 of an inch equals 1 foot, or could be used as a standard ruler. Works both ways. There are some scales that are 1/16 inch equals a foot. In the engineering scale, these are increments that represent drawings that represent entire sites and sometimes entire city blocks or city regions. In urban planning, for instance, the profession that I represent here at CAP, we use an engineering scale because many of our maps are at 1 inch equals 100 feet or 1 inch equals 200 feet in order to represent an entire city district on one sheet of paper. In those cases, if I'm reading a drawing or plan that's 1 inch equals 100 feet, I'm going to be using the 10 portion of the engineering scale and simply in my mind adding an additional 0 to the scale so that 1 inch would represent 100 feet. So I'm doing a little bit of math in my head in order for this to actually work for a drawing that might be at 1 inch equals 100 feet. 1 inch would mean 100 feet. I would add in my mind one additional zero here, but I'm actually adding two zeros here. Consequently, you can see the 50 flipped upside down there. In that case, it reads 1 inch equals 50 feet, and you can start to see upside down here, 0, 2 would represent 20, that's approximately half an inch, 40, 50, look at this. I'm reading this upside down, 0, 2, 4, but the 5 is in between the 4 and the 6. And as you can see graphically, that's approximately 1 inch. 1 inch equals 50 feet, represents these larger scales on the engineering scale. Now, the engineering scale, as I mentioned, is not just used by engineers, it's also used by landscape architects, urban planners, and any architect who is doing large-scale site work, because those drawings are much larger scales than what are found on the architect's scale. So you can see examples here of reading from left to right and right to left. In this case, the 3/4 inch equals a foot. That's a scale that we sometimes enjoy using for wall sections, portions of the wall materials that fit on a sheet of paper. 1'6" would be read either this way, either from 0 to 1 plus halfway between 1 and 2, or we can use the divisions represented to the left of the 0 to do that. We could use the 1 and then 6 inches there in order to reach a 1'6". There's two ways to read that there, but it works either way. The 3/8 inch equals a foot. We read from 0, 1, 2, 3, 4, 5, 6, 7, 8 feet, plus we have that additional space there to the left of the 0 in case we're measuring a line or space that is fractions of an inch as well as a nomenclature of feet. On the 1 inch equals 10 foot scale, as I mentioned before, there's a 0, 1, 2, and so in our mind we need to be mindful that this scale could represent more than one division of scale. We could be reading in tens, because engineers and surveyors do measure sites in tens. That would be 12 feet. That's 2 tick marks over the 1. Or we could start adding zeros and recognize that if we're reading this as 1 inch equals 100 feet, that's actually 120 feet. 100 is here, then 2 additional tick marks represent 20 more feet. So the 10 portion of the engineer scale is quite often used because it can represent 1 inch equals 10 feet, 1 inch equals 100 feet, or even 1 inch equals 1,000 feet. You simply just add 0 as you read it. Similarly, on the 1 inch equals 20 feet scale, we can add zeros to it to actually read drawings or plans that are 1 inch equals 200 or even 1 inch equals 2,000 feet if you're looking at the whole region of the Earth. Line types are important across the professions because they represent different things on maps and on site plans and drawings. And we typically try to keep these things consistent across the professions so that people don't get confused. And so hidden lines might be lines that represent something on an architectural plan, might represent an overhead plane, either in an interior architecture situation or in the case of a roof overhang, for instance. In landscape architecture, it might represent an overhead plane on a structure in the middle of a plaza or a park or something of that nature. Property boundary or site boundary, there's that dot dot dash line, which is not Morse code, but it is the different line types do become recognized across the engineering drawings and planning drawings, landscape architecture drawings, and architectural drawings because they mean the same thing to all of the different people. And so you'll see line types being used across these different professions. We try to keep them consistent so we can understand that at any drawing that someone produces, that a site boundary uses a particular line type. Line weight is extremely important for creating emphasis and the illusion of depth. We can see here as we look at these different lines that Probably, this one looks a little bit further away, and this one might looks closer to us. So by varying the line weights, when we start to create multi-view drawings, other presentation drawings, we are in fact giving the illusion of something that's closer to the viewer. And so good understanding and command of line weight will be critical for making successful drawings and beautiful drawings that start to create the illusion of depth. We talked about how industrial designers and product designers in the previous installment of our videos, how line weights were used to create emphasis to either create emphasis around an entire object or the object boundary. Typically in architectural drawing, lines that are closer to the viewer are typically drawn with a thicker line weight. Planes or edges that disappear behind solids, sometimes we enjoy the ability to see the hidden line behind something so that we don't lose the information that might be important to us. And then minor lines are thinner that are further away from the viewer are typically drawn with a lighter line weight. So in this drawing, the boldest line weights might represent the planes that are closest to us, but we could even emphasize around the entire figure at a bolder line weight. These interior edges would be a thinner line weight, and then the hidden line would represent those edges that we don't see but are important to us because they represent the continuity of the shape itself. Plan sections and elevations are orthographic projections that are necessary for communicating construction fabrication documents. The ability to measure a drawing in a construction set is critical for our fabrication team, our building team, to understand, to estimate and prepare the materials for construction. So we draw these things to scale so that they can be measured at scale and that they can be taken into the field and used to communicate with different members of the team. Plan is typically in a site planning situation or landscape architecture situation for either architects, landscape architects, or planners. The overhead view is looking directly down at a building here. We're looking at a Dutch hip roof in this particular case. The side elevation of that figure or that construct might show that the Dutch hip there angling up to the ridge line. You can see the ridge line is matching the view and plan. If we were to cut a simple section through that elevation, we might start to see the thicknesses represented of the joists as well as rafters and the walls, and we would crochet those portions that are solid to communicate to the viewer that we are in fact putting through portions of this that are solid, and understanding the mass void relationship. Back to our understanding of positive and negative space and how positive and negative space represents mass and void, that carries through into the conventions of architectural drawing. The ability to draw the overhead view or plan view, side elevation, both front and back together on one page is interesting to us because it allows you to start at any one of these points. You could very well start to draw in one of the elevations, project these lines up to a bisector, and then start to form the plan. You see how the front or back elevation of this figure, it lines up perfectly, and how heights are matched from the side elevation to the front. So it's really nice to be able to, whatever the figure is, whether it's an object, a building, or it's some other construct, to be able to construct them all on one page. And you can do so by using your T-square or parallel glider to match these different measurements so that things start to line up. And then you can see how this bisector here, you carry over the dimensions of the plan to the bisector, you can bring it down and actually match the top ridge line to here and then the far wall to there. Everything remains consistent in terms of its length. So it's helpful to start to think about how different orthographic views might occupy a page and how you actually construct them from one to the other rather than arranging them willy-nilly across the page. Other complex figures, this staircase here. So if we imagine this might be a concrete staircase that you pick up at a home center or it might be a Tetris block, if you've played Tetris in your life. If you look at it directly from the top with no perspective distortion whatsoever, it appears very simple as a rectangle with two additional lines in it, but you're actually looking at that top step surface of that top part of the thread, the second thread, the third thread, top thread, second thread, third thread, and you then see the edges between those threads. If you flip it around, obviously, you can see how this entire organization is flipped. If you look at it directly from the front, you're looking at each riser: first riser, second riser, third riser, first riser, second riser, third riser, and then a representation of the width of the stair, which in fact matches the measurement here. If we're looking at it from the back, our convention in multi-view drawings is to create a hidden line to remind our viewer that they are looking at something that's not just a solid box, that they are in fact looking at a stair-step or a stair-step construct from the rear. So we use a hidden line to represent the lines that we can't see. Same thing goes for the bottom view. If you're looking straight up at this stair-step construct, we would use hidden lines to represent, again, the lines that we can't see. Put them all together on a sheet, it gives you a more comprehensive picture of the complexity of this figure. And consequently, any one of these drawings is something that you could measure if you were to fabricate this. Remember that these drawings are intended to communicate not just to ourselves, not just to members of our team, not just to our clients, but to someone who needs to measure and estimate materials for fabrication. So often these drawings need to be able to be measured or calculated or otherwise. Put the drawings together, you can see how the top lines up with the side elevation, how the front elevation lines up with the side, and so on. Here's a little curveball now. So here is a rectangular prism that has a chamfered edge or beveled edge. From the top, you can't see the bevel because we're looking directly down at that edge there and then the front edge there. You can't tell that it's beveled whatsoever. Same with the front elevation of this figure. If we were to line that up perfectly, you can see that that's in fact a diagonal edge or an angled edge. That's not visible from the front elevation or the top. So often these drawings need to work together to communicate the reality of the object. Or we can add a paraline drawing off to the side that respects all of the true lengths of everything. Notice how these dimensions remain true to the figure here, and that starts to communicate the true nature of the object to the viewer. In two-dimensional drawings and communication that we would often transmit by mail or by fax or even by internet, these drawings come together to communicate the true picture to our fabricator. So in order to maintain clear communication, the drawings do work together to do that. Many of you are probably familiar with floor plans or have studied floor plans or are fascinated by floor plans, as I am. They are, in fact, a horizontal section cut through a series of spaces and solids. So if we were to imagine sending a picture plane right through a building, pulling off the top, leaving the bottom, this picture plane acts almost like a knife as it's cutting through this particular residential structure. As it cuts through solids and voids, we tend to poche or shade the solids, the portions that are the walls, to represent them as solids, and then leave the rest as voids. And then nomenclature is used, different symbols and blocks, or otherwise, we call them CAD blocks now. Furniture is used to help indicate the intended use of this space or the scale. So all those things start to come together to represent architectural space, or interior space in these cases. We call this poche because it's just like putting your hand in a pocket. Poche is the French word for pocket, and pocket is the mass in between two layers of something, just like putting your hand into a pocket, which is two layers of fabric. We poche the solids to represent the solid portion of the building that has the solid walls. This makes it readable to the casual viewer to help us understand where the windows are, where the doors are, and where the voids are. In a site plan, we're looking, it's as if we are a bird flying over the site, looking straight down at it. And so all of the measurements or dimensions are measurable to a scale or drawn to a scale. You can see a scale bar and a north arrow down here. And then we have a series of conventions in landscape graphics to represent one material from another. This might be water, these are stone, these are plants, this might be lawn or sand, this might be a terraced lawn. Here we're going up to a slight little mound. These might be ornamentals, these might be evergreens or conifers. And those are drawn together with representations of texture, tone, and shadow to start to create the illusion of depth as we move through the space. I can see that I can probably occupy this lawn. I can walk around, sit on this bench, look at this portion here, look at the waterfall, maybe walk under the tree, and either enter or exit the building. In this case, a little bit different nomenclature. We sometimes find it important at architectural scales. This might be drawn at 1 inch equals 10 feet, or 1 inch equals 8 feet, or even quarter inch to be consistent with residential architecture. But an overhead deciduous tree sometimes covers up so much of the view. Well, it is overhead. Well, let's draw that tree as if it were transparent to indicate to the viewer that most of the tree is overhead and that we can walk under it and still represent more plant material underneath it. So often when you look at landscape architecture drawings, you can be able to tell trees apart very easily. These might be evergreen or conifer trees. You can see it kind of reads like a chimney sweep or a chimney brush, and it's casting a cone-shaped shadow. In this case, overhead deciduous trees are things that we can like reach full fruition, are things that we can walk under, and we can still represent materials underneath that transparent representation of the tree's canopy. Also, as deciduous trees get bigger, they tend to cover up a lot of the drawing. We tend to lose a lot of the drawing there. So again, that's another reason why we represent the trees in that fashion. Sections through buildings or sections through landscapes are extremely important to represent the different levels and different topography or different features of either an architectural project or a natural site or a constructed site, or any combination of those things. Landscape sections are really interesting because we like to bold up the double line, really thick line here, to basically tell our client, imagine a knife cutting through the earth and then revealing or pulling away the foreground so that we can understand exactly how these different spaces and how these different features of the site are sitting on the cut of the earth or sitting on the topography of the earth. So we've got a cabin here sitting on a little bit of a hump, a big boulder here with a little bit of a valley. We've got a rural road here built on this particular hump, reinforced on both sides. More boulders or stones representing the stream bed here, probably either a stream, river, or pond, and then even the representation of this waterfall here. This is probably a very scenic situation with representation of the background, using line, weight, tone, and texture to create the illusion of depth. This really thick, bold line here really pops and really helps us understand this is exactly the foreground of this particular view, and helps us remember that we are cutting through the earth, pulling it away to represent it as a cross section. So it's very similar to the poché that we use in architectural sections to communicate the solids that we are in fact cutting through. Again, this is from Frank Ching's book. This is from Grant Reed's book, by the way. This is from Frank Ching's book. The picture plane, if it were to be inserted into the middle of the building, would look something like this, and that we are cutting through the solids of the building materials there and seeing and understanding the space and scale of the fluids. So always think about, remember that a section is a cut through a complex space, landscape, or object or construct, we pull part of it away and we look at it from one side to help us understand the scale and dimensions of the spaces that are there. Elevations are projected drawings, everything at a representative length to the scale of the drawing, looking straight at it. There's no perspective distortion present here. So objects or spaces or constructs that project off of this house are not vanishing whatsoever. So we can understand the scale of this porch and the scale of this solarium. Where I come from, we call these Michigan rooms, Michigan, are represented all at scale to one another. There's no perspective distortion whatsoever. There is a cut here similar to the site section we saw before. There's a nice bold line here that represents the slight topographic change that might be on the site. And you can see how the architect has responded to that by making the floor level probably consistent and allowing the basement level to disappear below grade. You can even see this perhaps stepping down to the sidewalk level here on the edge, the street edge. In Frank Cheng's book, here's another example of looking at the side of a particular building, looking at the front. This is a simple gable house with a shed roof attachment to it, and you can see how the foreshortened edge or angled edge of that particular extension shed roof over the porch. Its dimension from this point to this point here is representing the front elevation as from this edge to this edge. Frank Cheng always loves to add extra shadows and things like that, just to really give kind of a grasp of the reality of the situation, and give you more character in terms of what these different drawings can do. Another category, according to Cheng, paraline drawings. We have Exonometric drawings, an umbrella term for isometric, diametric, and trimetric. Foreshortening is illustrating an object closer than it is, having less depth is an effective perspective. And so by foreshortening edges, we can make an object appear angled to the viewer and allow our viewer to experience or see a series of objects or spaces in this, what we might call a three-quarter view. It gives us more of a bigger picture of what an object or space might be. But there are three types of drawings under the exonometric category: isometric, diametric, and trimetric. Isometric, three main axes make equal angles and are equally foreshortened. Isometric is one of the more popular views in gaming, so some of you probably play games that are in the isometric view. We can see this figure here. This is probably a cube. All of the edges are at the same length, but the three main axes make equal angles to each other and are equally foreshortened. So this angle is the same as this angle, and they are equally foreshortened. It provides that perfect three-quarter view. In a diametric, one of the axes is either elongated or foreshortened. Everything remains at true length, but you can see that the one plane of this cube is more foreshortened than the other. And this is helpful if you're favoring one side of a building or construct versus the other. It gives you a different character of a drawing versus the isometric, which has equal foreshortening on the planes. Trimetric, all three axes are foreshortened at a different rate and scale. And trimetric, I can't recall doing a trimetric drawing recently, but this unequal foreshortening is if you were definitely favoring one side of the structure versus the other two sides. And you can see you can see the top plane is quite foreshortened, so it would favor basically these two sides of the construct versus diametric, which still kind of feels like we're looking down at it. Oblique drawings, a principal face of the object is oriented parallel to the picture plane, but is projected at any other angle than 90 degrees. Well, in the oblique, you can see one of these three visible planes of this cube remains true. It is still a square. Aha! That hasn't been foreshortened at all. Look back at the isometric dimetric and trimetric, you can see the top plane of this cube has been foreshortened. But in this oblique view, that top view of the cube remains true. It is still a square. It's just been rotated, probably to line up with 30, 60, 90 triangle. That looks about 30 degrees there. That looks about 60 degrees there to the parallel. And so by simply turning that square and projecting these lines down, we have an oblique view of that particular cube. So we often use plan oblique to make drawings that start to show the different spaces and complexities and features of a space. We may have pulled off the roof in this case, but you can see Ching here has taken a plan view, rotated it 30 degrees using a 30, 60, 90 degree triangle, started to project up these columns and walls, and we can start to see a better picture of what is the intention for the space. Here's the same idea using a 45, 45, 90 triangle, and here it is slightly different. You can see the 60 degree angles here, the 30 degree angles here. Using that same 30, 60, 90 degree triangle, the 60 degree part of the triangle is there, the 30 is there. And you can see each way here, there's a different character to the drawing in terms of understanding the space that's being represented here. So plan oblique is quite a popular drawing because you can take your floor plan, rotate it slightly, and then project elements up. It's quite useful in landscape architecture and urban planning drawings as well, because the plan remains true. Perspective versus orthographic projections. In perspective projection, things vanish away from us. In orthographic projections, things are projected true. So the biggest difference between orthographic drawings and perspective drawings is the nature of how this view is representing the space or the object or the landscape. And as we know from elevations and plans that these things do remain true. In perspective, everything vanishes away from us to enhance that illusion of depth. Picture plane, as Ching describes it, is the invisible plane by which all of these edges and lines are projected versus the viewer who sees them through that invisible plane. So I've seen a few of you walking around the second floor recently during studio time, holding up a piece of plastic and starting to create drawings by holding up that sheet of plastic and then using a dry erase marker to map out your drawings. That, for those of you who are drawing with that piece of plastic, you're actually using a picture plane. That is the picture plane itself. It is the invisible plane by which we can see contours and edges. And so really good to help understand how the picture plane starts to become an element in how these drawings come to be. When we make perspective drawings using traditional methods, Frank Ching is representing here what we typically call the office method. It's a method of perspective drawing that folks have been using since the Renaissance. We have terms such as the station point, or where the viewer might be standing. So if we look at this overhead plan of this building, we are establishing that the viewer will be standing at a station point. Sight line, or a line of sight, represents the primary line of sight from the station point viewer to the object. Central axis of vision. Cone of vision, we typically have a 60-degree cone of vision by which we can use to represent an object, space, or construct. So this perspective drawing that Ching has here is representing a 60-degree cone of vision from the viewer. That's our typical cone of vision. That does not include your peripheral vision, but your typical cone of vision is approximately 60 degrees. The picture plane is that invisible plane, which in this case is placed right at the edge of this house, and so therefore all of those edges, when they when they go from the station point to the furthest part of the house, when they hit the picture plane, that becomes the first line. So the office method perspective drawing has to know the distance of the viewer to the object and the placement of the picture plane in order to make the drawing happen. The horizon line, where everything vanishes to, in this case, a two-point perspective. Things vanish to a vanishing point on the horizon line, which might represent the curvature of the Earth or the edge of the Earth. The ground plane, the portion of the drawing that represents the ground that we stand on. And then the ground line, which the object sits on. The ground line is what closes out the perspective. So to review, this slide deck from John has summarized chapters 5 through 7 in Design Drawing by Ching and Jurasik. So we hope that this summarizes well all of the different nomenclatures, terminologies, drawing conventions, and drawing types that are found in chapters 5 through 7. So please review chapters 5 through 7.